Welcome back to Bitwise Smarter, where Python becomes less scary and slightly more chaotic. Today we are learning functions that take inputs, functions with outputs, dictionaries, nesting, and then we'll build mini projects, an office snack poll where everyone votes. If you have watched parts 1, 2, and 3, you're ready. Let's jump in. Section 1, Functions, Basic plus Inputs. A function is basically a recipe with a name. You write a set of instructions once, give it a name, and then tell Python to run it whenever you need. Instead of rewriting the same steps again and again, you say, "Hey Python, do the thing." Example 1, Simple functions, no inputs. Let's make a function that powers up your developer mode. Def means define. We are telling Python, I'm about to define a function. Python does nothing yet, it's just listening. Developer mode is the name of the recipe. This is how Python will remember this set of instructions. Later, we will say developer mode, parenthesis. Python will know what to do. Function name should describe what the function does. The parenthesis means inputs. Right now, the parentheses are empty. That means this function doesn't need any information from outside to run. We'll add inputs later. The colon starts a block. This tells Python everything indented below belongs to this function. Indentation is extremely important. Python uses indentation instead of brackets. Every indented line belongs to the function, will only run when the function is called. Important concept. Here's something beginners often miss. Python does not run this code when it sees the function definition. Python just stores it in memory. Nothing happens until Python sees this line, developer mode parenthesis. This line is the trigger. This is when Python actually executes every line inside the function top to bottom. Let's run this. This output appears only because we called the function. Here is a mini challenge. Create a function called launch sequence that prints 3 lines, like a rocket launch. Pause here and try it. Here is a probable solution. Let's run it. This follows the exact same pattern as before. We define the function, Python stores it in memory, nothing runs yet. We call the function, Python executes every indented line in order. There is no magic, just definition, memory, execution. If you understand this flow, you understand the foundation of functions. Now let's look at inputs, parameters versus arguments. Right now, a function always does the same thing. Every time we call developer mode, the output is identical. But real programs need flexibility. That's where inputs come in. Inputs let us pass data into a function, so it can behave differently each time. Same recipe, different ingredients, different results. Let's look at an example. Functions with one input. Here, name is a parameter. Think of it as a blank label. It doesn't have a value yet. Praise Rico, praise intern number 7. Name is a parameter, a placeholder inside the function. Rico and intern number 7 are arguments, the real values we pass in. When Python runs praise Rico, it temporarily replaces name equal to Rico everywhere inside the function. Then, when we run praise intern number 7, Python replaces name equal to intern number 7. So the function itself never changes, only the input changes. Same recipe, different ingredient, different output. Let's run it. Here is another challenge. Write a function called greetCity that prints, "Hello, how's life in city?" Pause here and try it. Here is a probable solution. Let's run it. When we call greetCity Tokyo, Python does the following step by step. It creates a variable called city. It assigns it the value Tokyo. It runs the function body. Everywhere it sees city, it uses Tokyo. So this line, print how's life in city, becomes print how's life in Tokyo. That's it, nothing fancy, just replacement and execution. Section 2. Two inputs plus argument types. So far, our functions could take one piece of information, but real-world situations usually need more than one thing. For example, a name and a snack, a person and a destination, a number and another number. In Python, a function can take multiple inputs. You just need to separate them with commas. Let's look at an example. Functions with two inputs. Let's run it. Let's slow this down. Inside the parentheses, we have two parameters, name, snack. Think of these as two empty boxes. The function doesn't know what value they'll hold yet. It only knows when someone calls me, they must give me two things. Calling the function. Correct order. Introduce Maya, spicy chips. Python sees Maya first, assigns it to name. Python sees spicy chips second, assigns it to snack. So inside the function, Python temporarily treats it as name equal to Maya, snack equal to spicy chips. Then it runs the print statements using those values. Positional arguments. Order matters. Let's run this. Introduce spicy chips, Maya. This code does not crash. Python does exactly what you asked, even if it's wrong. Python does not understand meaning, it only understands positions. So Python says first value goes into name, second value goes into snack, which means it becomes name equal to spicy chips, snack equal to Maya. That's why the output looks strange. Python isn't being smart or dumb, it's being literal. Beginner warning. This is one of the most common beginner mistakes. Your code can be syntactically correct but logically wrong, and Python won't stop you. Next up is keyword arguments. Order does not matter. Let's run it. Introduce snack equal to spicy chip, name equal to Maya. Now we are telling Python exactly where each value belongs. We are saying name should get Maya, snack should get spicy chips. Python no longer relies on position. It matches values by parameter name. This is safer, this is cleaner. This is how real-world Python code is often written. When to use keyword arguments? Keyword arguments are usually helpful when functions have many inputs. Inputs are optional. Order is confusing. Code readability matters. Here is another challenge. Create a function called travel plan and call it using keyword arguments. Pause here and try it. Here is a probable solution. Let's run it. Here we define a function with two parameters, person and destination. These are placeholders. They don't have values yet. Travel plan, destination equal to Iceland, person equal to John. Python sees destination equal to Iceland, assigns Iceland to destination. Python sees person equal to John, assigns John to person. Order does not matter anymore. So inside the function, Python behaves as if it wrote person equal to John, destination equal to Iceland. Then it executes the print statement. Section 3. Functions with outputs. Return. So far we have been using print, and print is fine, but print has a limitation. Print only shows something on the screen. Return actually gives the value back to the program, so it can be reused. A good way to think about it is this. Print is like shouting the answer out loud. Return is like handing the answer back so it can be used later. Let's look at an example. Function that returns a value. Let's run it. Let's walk through this very slowly. We define a function called double points. Inside the function, we take an input called points. We multiply it by 2. and then we return the result. Score equal to 7 print score. Python calls 7 points temporarily become 7. Python calculates 7 multiplied 2 giving 14. Return 14 sends the value back. The function call is replaced by 14. So this line score equal to 7 becomes score equal to 14. That's the key idea. The function call itself becomes the returned value. A function with return is not just doing something, it is producing a value that the rest of your program can use. Let's look at another example, name formatter, cleaning plus formatting. Let's run it. This function does three things in order. It cleans the input. Strip removes extra spaces. It formats the input. Title capitalizes properly. It returns a final formatted string. Notice something important. There is no print inside the function. Name equal to format display name Alice, wonder, print name. This makes the function reusable. We can print it, save it, send it to another function, store it in a variable. The function doesn't decide how it's used. It just returns a clean value. Functions that return values are building blocks. You stack them together to build real programs. Here is another concept, chaining function outputs into inputs. Now, here's where functions with return start to feel really powerful. Because once a function returns a value, that value can be used anywhere a normal value can be used, including as the input to another function. Let's look at an example. Let's run it. Let's slow this way down and walk through it like Python does. Step 1. First, Python sees this part, echo hello. Inside echo, text becomes hello, text plus text becomes hello hello. That value is returned. So this line, echo hello, becomes hello hello. Step 2. Output becomes input. Now Python takes the returned value and immediately passes it into make underscore title. So this make title echo hello is treated as make title hello hello. Step 3. Make title runs. Inside make title, dot title capitalizes each word. The result becomes hello hello with capital H. The value is returned. Step 4. Final assignment. So now this line final equal to make title echo hello becomes final equal to hello hello, and therefore we have the final output with hello hello with capital H. Now let's look at a very important concept, early return and multiple returns. When Python sees the keyword return, the function stops immediately. Nothing after return runs. That means we can use return to exit early when something is wrong. Let's look at an example. This function has two possible return paths. Let's break it down. Case 1, bad input. Print say full name null, Skywalker. Here's what happens. First dot strip becomes an empty string. The condition is true. Python hits the first return. The function immediately exits. The second return is skipped. The output becomes please enter both first and last name. Case 2. If both names exist, the if condition is false. Python skips the first return, Python reaches the second return and returns the formatted name. Let's run both these examples. A function can have multiple return statements, but only one of them will ever run. As soon as Python hits return, the function is done. Here is another mini challenge. Write a function called saveDivide that refuses to divide by 0. Pause here and try it. Here is a probable solution. The function protects itself from bad input. Here's the logic. If b is 0, dividing would crash the program. So we return a warning message and exit immediately. If b is not 0, we safely divide and return the result. Let's run it. This is called defensive programming. It means don't trust input, assume users will make mistakes, protect your code before it breaks. Real programs do this all the time. Section 4, Docstrings. So far, we have been writing functions that work, but imagine coming back to your code 6 months later, or imagine someone else on your team trying to use your function. They'll ask, what does this function do? What kind of input does it expect? What does it return? That's where docstrings come in. Docstrings are built-in documentation for your code. They live inside your function and describe what the function does, what kind of input it expects, what kind of output it returns. Let's look at this example. Let's break this down. The docstring is the very first thing inside the function. Uses triple quotes, can span multiple lines. Is not a comment. Python actually stores it. This means tools like editors, debuggers, help, autocomplete can show this information automatically. A docstring is not for the computer, it's for future you, teammates, anyone using your function. Good programmers write code that works. Great programmers write code that explains itself. Section 5, Dictionaries. So far we have used lists. Lists store values by position. Index 0, index 1, index 2, but many real world problems don't work by position. They work by meaning. A dictionary stores key value pairs. Instead of asking, give me item at position 2, you ask, give me the value for this label. Think of a real dictionary, word mapped to a meaning, contacts, a name mapped to a phone number, settings, options mapped to values. You don't care where the item lives, you care about what's it called. Let's look at an example. Let's run it. Each entry has a key, the label, a value, the data associated with it. Keys are usually strings. Values can be anything. Now to access the values, let's look at this line. This means go into toolbox, find the key called Python, give me its value, and the output shows as automates everything. Now let's look at adding editing dictionary entries. Here is an example. Let's run it. These two lines do two possible things. If the key does not exist, it adds it. If the key does exist, it updates it. Same syntax. Python decides based on the key. Here is another concept, looping through a dictionary. Let's run this example. When you loop through a dictionary, Python gives you the keys by default, not the values, not both, just the keys. So the pattern is loop, get key, use key, get value. This pattern is extremely important and used everywhere. Here is a mini challenge. Create a dictionary called pet sounds with three animals and their sounds. Then print each animal and sound. Pause here and try it. Here is a probable solution. Let's run it. Each animal is a key. Each sound is a value. Animal becomes cat. Pet sounds of animal becomes meow. Then dog for woof. Then cow for moo. This loop walks through the dictionary one key at a time. Section 6, Nesting. Nesting simply means putting collections inside another collection. For example, list inside a dictionary, dictionary inside a dictionary, list inside a list. Think of nesting like real life. House, room, drawer, item. You don't jump straight to the item. You go layer by layer. Let's look at this example. Let's run it. Here, keys are days. Values are lists of activities. Now, to access nested data, let's look at this line. Let's break it into pieces. Watchlist weekday gives us the list. The number 2 gives the item at index 2. So the final result gives us more emails. Always read nested access from left to right. Here is another challenge. Print nap from Friday. Pause here and try it. Here is a probable solution. Let's run it. First, get the schedule list. Then, get item at index 2. Break it into steps if it ever feels confusing. Now let's look at the final concept for this video. Dictionary inside dictionary plus list inside that dictionary. Here is an example. Let's run it. This is a nested structure. Player profile is the main dictionary. Stats, dictionary inside it. Inventory, list inside that dictionary. Now to access deeply nested data, let's look at this line. Player profile stats gives this part. Inventory gives this part. The number 2 gives banana. Each bracket moves one level deeper. If you ever feel lost with nesting, stop, break it into steps, print immediate values. That's how professionals debug nested data. Alright, it's project time. You're going to build an office snack poll using Python. Your program should ask people for their name and which snack they want to vote for. You'll store those votes in a dictionary where the snack name is the key and the vote count is the value. After each vote, ask if there are more voters. When voting is done, your program should figure out which snack got the most votes and print the winner. Pause the video here, try building it step by step, and don't worry if you get stuck. Thinking through it is the win. When you're ready, press play and we'll solve it together. Here is a probable solution to the mini project. Let's look at the big picture. We are building a simple voting system. We want to let people vote for snacks, count votes quietly, store them neatly, and announce the winning snack at the end. To do this, we'll use a dictionary to store snack, a loop to keep asking for voters, a function to figure out the winner. Let's break this down. Part 1. The winner finding function. This function has one job. Look at all snacks and figure out which one has the most votes. It takes one input, a dictionary. One function, one responsibility. That's good design. We are setting up scoreboard. Highest votes keep tracks of the biggest number we have seen so far. Winning snack stores the name of the snack in the lead. We start at 0 because votes are always positive. When you loop through a dictionary, Python gives you the keys. So if dictionary is chips 3, cookie 1, Python loops through chips first, then cookies. Votes equal to vote dict of snack. Your snack is the key. Vote dict of snack gives us the value, the number of votes. So now votes holds the count for the current snack. This is the core logic. We ask, is this snack beating the current leader? If yes, update the highest vote count, update the winning snack. Think of it like updating a leaderboard. After checking every snack, we print the final winner. Part 2. Starting the program. Just a friendly intro for the user. We start with an empty dictionary. This will slowly grow as people vote like chip 2, fruit 1. This is a control flag. As long as it's true, voting continues. When it becomes false, voting stops. Part 3. Voting loop. This loop runs once per voter and only stops when we say no. We collect the name for realism. It doesn't affect counting. Dot lower is important. It prevents bugs like chips with all caps or chips with all small letters. All becomes the same key with dot lower. Part 4. Counting votes. We check, have we seen this snack before? If not, we create it and start its count at 0. Vote snack plus equal to 1. This adds 1 vote. 0 becomes 1. 2 becomes 3. This single line is the heart of vote counting. Part 5. Continue or stop. We ask if voting should continue. Again, normalizing input. Printing blank lines pushes previous content away, simulating a clear screen so votes stay private. If the answer isn't yes, we stop the loop, pass the entire dictionary into our winner finding function, and that's how we announce the final result. Let's run it. And that's a wrap for part 4 of Python for Beginners on Bitwise Smarter. Today, you didn't just learn concepts, you used them. You learned how functions organize your code, return values, pass data around, dictionaries store and count information, loops keep programs running, and how all of these pieces work together in a real project. The office snack poll might look simple, but it uses the same logic you'd see in real world systems like voting apps, surveys, and analytics pipelines. In an upcoming video, we'll build another project, the calculator, where we'll push this even further by storing functions inside dictionaries and chaining calculations like a real calculator. If this video helped you, like it, share it with someone learning Python, and subscribe to Bitwise Smarter for more such videos. I'll see you in the next one.